Welcome, everybody. Thanks for being here. So this is our weekly meeting, and we have the pleasure to have today Ana Martín with us, and she let me just say a few words. She just became a doctor in last summer, and she's now pursuing a postdoctoral position in the Universidad del País Vasco, and also she's member of a startup, founding member of Quantum Maths, which is a company devoted to quantum software. Well, she's an expert in digital analog quantum computing. So we were glad to have her here to give us an overview of the state of the art, and in particular also of her personal findings in this field. Without further ado, please, Ana, floor is yours. Thank you very much.
Thanks. Thanks to you actually for having me here and for inviting me to share my work on this topic on digital analog quantum computing. In fact, I'm going to share with you a part of my thesis, so the work that I have developed during the past several years, and I hope that you find it as interesting as I do. So I don't know if you can see my screen, the good one.
Yes, perfect. Go ahead.
Okay, a ver. Okay, so hello everyone. My name is Ana Martín, and I am now a researcher at the Inquiry Center, which is part of the University of the Basque Country. As I said, what I'm going to present to you is my work on digital analog quantum computing and algorithms, and I hope that you enjoy. Let me see. Okay. So, which are you seeing the main? Are you seeing the present?
We see perfectly.
Okay, so one slide at a time, right? Because I have two monitors.
No, one slide at a time.
Okay, perfect. So, thanks. So I will start briefly by introducing the concept of digital analog and the need of this new computational paradigm. After that, I will formally introduce the concept of digital analog quantum computation, focusing on the fundamental concepts and showing a simple but a representative example of how can it be employed for quantum algorithm implementations. I then will present a noise model that encapsulates most relevant noise sources in the NISQ devices so that I can come back later and compare the performance of the paradigm using both digital and digital analog approaches. Then I will show the implementation of several quantum algorithms, such as the Fourier transform, phase estimation, and the Harrow-Hasidim-Lloyd. And then I will show how to implement this algorithm using both digital and digital analog paradigm. And in order to test their performance, we will simulate. Yes, so in order to test the performance, I will show the result of both simulations, and let's see how resilient is its paradigm. Okay, so first, let me start by explaining what I mean by this computational paradigm, which is a concept that I will repeatedly use during my talk. So I am just referring to the criteria that is behind the implementation of an algorithm. So depending on the building blocks that one is using to implement a quantum algorithms, one could be talking about digital quantum computation or digital analog quantum computation. The most extended computational paradigm is the digital quantum computation. And the building block that it uses is single qubit gates to change the state of a qubit and 2 qubit gates to create entanglement and superpositions. This is the paradigm that has been widely used and has shown high fidelity rates in the implementation of short depth quantum circuits using NISQ devices. But these devices, these near intermediate scale quantum computing, so NISQ devices, they are affected by experimental limitations in the sense that they are not yet fully error corrected. So the noise that they face limits their computational power. So although this paradigm has shown high fidelity rates, it has to face some drawbacks, which I'm going to focus in the two main drawbacks of this paradigm. The first one is related to the resources that one needs to implement long depth quantum circuits. So if the quantum routine that one wants to implement is excessively large, there is a probability that this NISQ device cannot satisfy that demand. The other problem of the paradigm is in the noise rates that the 2-qubit gates present. So there is a sensible error that appears whenever this 2-qubit gate is switched on and off, and that error accumulates along the entire process. For example, if one wants to implement a n-qubit quantum Fourier transform, where n is a large number, there is a big chance that we are not able to perform it without facing noise-related error. But why does this happen? So let's analyze what is happening in the quantum processor whenever a 2-qubit gate is applied, and why is this so a noisy process. So whenever we have a quantum system, say superconducting circuits, trapped ions, Rydberg atoms, whichever the platform is, there is a natural interaction that arises between the particles that compose it, in this case, the qubits. When we perform gate-based quantum computing, the 2-qubit gates are, so to speak, natural operations in the sense that whenever this gate is performed on a pair of qubits, the interaction among them is maintained, while the interaction with the rest of the qubits of the system should be as attenuated as possible. Preferable, it should be null. If the interaction with the rest of the qubits of the system is not well attenuated, then the logical 2-qubit operation won't be well implemented, and that will translate into errors in our quantum routine. These errors are the one that accumulates throughout the entire process and lead us to this noisy outcome of the whole operation. It is true that one can use quantum control techniques to diminish as possible these noises, but these techniques are not scalable. So whenever we want to implement a long depth quantum circuit or we want to scale them, we are going to face the same problem. So going back to this image of our quantum system and the natural interaction that is always present among the qubits that forms it, it seems natural to get advantage of this interaction to perform quantum simulations. And that way, we can get rid of the errors that arises whenever we try to avoid it. And that is precisely the main idea of the DAQC paradigm. So the digital analog computational paradigm makes use of the natural interaction among the elements that conforms the quantum system to perform the quantum simulation.
Anna, can I stop you a moment?
Yes.
Yeah, we have some problem with your screen. No, it's okay. You should share it again. Only,
okay.
I think it's when you move the mouse or something like that, we get
yes.
a screen on top of the. So we get some. So try to just touch the least possible the screen, because we're getting some double image.
So you see both.
No. We get the screen, and then on top of that, a reduced version of your desktop. So it's a strange effect, but I've noticed that it only happens when you move your mouse, try to something like that. So just try to just stick to moving ahead the slides and not moving not touching the mouse, I think.
Okay, let's see. Let's see. So you you don't see the presentation now?
Now, yes. Okay.
And if I go,
yeah,
if
yes,
I click,
if you click the mouse, then we see something which is we see a reduce. We see one on top of the other. Yeah. So never mind. So it's just try to put the slides one after the other, and don't try to point to something. Yeah, because then it's wrong.
Okay, so if I have to click to
click
pass.
Yes, if you click,
so
well,
if I
it will be the minimal thing. Yeah.
Okay.
Then it goes back to it's a strange effect. I don't know how it comes.
Okay, let's see. So if, for example, I'm going to click to make this animation, do you
Yeah.
see this weird effect?
Yeah, for a moment, exactly. Then we get a strange effect. Yeah, I don't know exactly why. Yeah.
That is inconvenient because I have to click. I have to make this clicking.
Okay, don't worry. I mean, it's not too bad. It's not too bad.
Let me try to make it better, maybe in the sharing. Let's see.
No,
can I try to make it better?
Yeah. I think there's nothing you can do. I mean, just we'll stick to it. We see
maybe
this
I can
much
try
better,
to
a little bit reduced.
Let's see if I. Let me try to share instead of the. Let me see. Instead of the desktop, maybe I can share the application. Here, let me see. But I don't know, the problem is I have these annotations from the defense and I don't know if you're going to see the good screen or the presentation.
Yeah, no. Here we're seeing everything. No.
Yeah, I see.
No. It's better to go back and do the whole thing.
Or maybe I can try. Yeah.
Okay. Go back and we'll stick to it. It's not too bad. I mean, we can read it anyhow.
Yeah.
Yeah. Don't worry. Share the whole screen.
One. Okay, or if not, maybe can I try a last thing? Are we good on time?
Yeah. Okay. Yeah.
Stop sharing and then let's see. Maybe I can try. Let's see. Last time, and if not, we go back to what we had. Share, and then I share the keynote. And let's see if I managed to get rid of the notes.
Yeah.
Now you see.
Seems okay.
Yeah, is it okay?
Thank you.
Okay, then I have to change the monitors. Okay. Okay. And if I do the clicking.
Yeah, it's okay. It works. It works.
No double nothing.
Perfect.
Okay. Okay, I think I was over here, right?
Yeah.
Okay. So as I was saying, sorry for the interruption. As I was saying, the digital analog take advantage of the natural interaction that are within the system. So as the building blocks, the paradigm uses single qubit gates performed on top of the qubits, and these are the digital pulses. They have a fixed time. And the analog blocks of controllable time, in which the system evolves naturally according to the natural interaction that is among them. So this way, the digital analog merges the flexibility of the digital quantum computation with the robustness of analog simulations. Okay, so now that I have shown you how this paradigm works, let me show you how to use these techniques to make Hamiltonian simulations. So to do so, we are going to use two key components of the digital analog paradigm. The first key component is the ability to accurately evolve for a specific time, t, with the interaction Hamiltonian, and at the same time incorporating local rotations to create the evolved Hamiltonian H prime. Also, we will use Trotter decomposition to simulate Hamiltonian with non-commuting terms. And in this case, the error that we are introducing is of order delta t squared, where delta t is the time that the single qubit gate takes to be applied. Also, there can be used more advanced decompositions like the geometry size Trotter, and this will reduce the error to order delta t to the third. I think that the best way to to understand how can we use these techniques to simulate a Hamiltonian is by using an example, and this is the simple example that I told you before. So let's say that we want to simulate an inhomogeneous all-to-all two-body Hamiltonian, two-body Ising Hamiltonian. As resources, we will use single qubit gates. This will be the digital pulses applied on top of the qubits. And the natural interaction among the qubits of the system will be the homogeneous Ising Hamiltonian. This will be the analog blocks. So our goal is to simulate this all-to-all two-body Ising Hamiltonian with arbitrary couplings. And for simplicity, we are going to assume one thing that we are going to use is superconducting circuits as the quantum platform, and also that the qubits that conforms it has the following connectivity. So they have all-to-all connectivity with an homogeneous coupling constant, G. So in the end, the interaction Hamiltonian would be the one that I'm showing you here. What we are going to do is what follows. First, we're going to apply digital pulses onto qubits. Then we are going to let the system evolve during a certain time, T1. And finally, we are going to apply digital pulses on the same two qubits at the beginning. And what I am doing when I sandwich the time evolution between these digital pulses is, in essence, change the terms of the Hamiltonian that describe the system. If we look at what happens when we apply the single qubit gates on before and after the time evolution of the Hamiltonian, we see that we have introduced this constant T1 over each two-body term. And this T1 is followed by a plus or a minus sign.
Mm-hmm.
If I rotate, if I do this to the first and the third qubit before and after letting the system evolve during a different time, T2, we see that the same thing happens. Mm-hmm. There appears this constant over each two-body term. And the same thing happens if I apply the single qubit rotations over two different pairs, the second one and the third one. So if we do this operation one after the other, the operation is described by this unitary operator, where each two-body term is multiplied by different linear combinations of the interaction time, T1, T2, and T3. So remembering that the Hamiltonian that we wanted to simulate is this homogeneous Hamiltonian, it is easy to see the relation between the one that we have achieved and the one that we want to get. Mm-hmm. So the linear combination of the analog interaction times are playing the role of the different coupling constant of the homogeneous Hamiltonian. Mm-hmm. One moment, I need to have some water. Mm-hmm. Okay. So in the end, the entire problem reduces to find an appropriate map between the simulation time by the coupling constant, the inhomogeneous one, and the coupling constant of the system by the time of each evolution of each analog block. And we do this by slicing the unitary operation into several analog blocks of different time length and sandwiching this evolution between local rotation, in this case around the x-axis. Mm-hmm. And finding the duration of those analog blocks is just a matrix inversion problem, where the matrix M is a signed matrix n by m. And this is non-singular for all value of n, which is the number of qubits, except for 4 qubits, which in the case of 4 qubits, we will apply different set of single qubit rotation, but we could also get a solution of this problem. Mm-hmm. So it is possible to use similar methods to systematically build the evolution of any completely general Hamiltonian with interaction that can go up to m-body interaction, m-bodies interaction. Yes. And the procedure is detailedly explained in this work by Adrian Parra and collaborators. And here there are a lot of different Hamiltonians and different digital analog techniques to simulate them. So what I have shown until this point is what is known as the stepwise version of the digital analog paradigm, where the interaction is switched on and off between the digital blocks. Under ideal circumstances, meaning that we don't have any noises or experimental error, this would lead to the same state as the digital method. So doing this and doing the digital implementation should suppose no difference. We should get the same result. But there is another approach, which is called the bank DAQC. And in this case, the analog interaction is on during the whole simulation, and the single qubit gates are applied on top of this interaction. So the total amount of time in which the analog block is on in the bank approach is the sum of the different analog blocks that we have found in the stepwise protocol. But the difference is that here, under ideal circumstances, the bank protocol does not generate the same result as the stepwise or the digital, since there is an intrinsic error on the bank which does not depend on the experimental conditions or the noise sources. This error is due to the superposition between the Hamiltonians of the single qubit rotation and the analog Hamiltonian. However, if the time that takes the single qubit rotation is much smaller than the times that takes its analog blocks, we can assume that this error scales up much better than the noise errors that we will face using digital or the stepwise digital analog version. And this is what we are going to test by doing different simulations.
I see.
So what we have done was to define several quantum algorithms using both digital and digital analog versions, and then test them under the noise framework that we have sort of designed. But this is a framework that takes into account sensible noise errors that one could face in the implementation of different algorithms used in different quantum platforms. So we had taken into account single qubit gate error. This error would affect both the digital and the digital analog version. Then the 2-qubit gate control error. This only affects to the digital version since the building blocks are single and 2-qubit gates. And then for the digital analog, the other error that would take some importance would be the analog block control error. And then we also included different noise sources that affect both paradigms, which is the bit flip channel, the measurement channel, and then the amplitude damping channel. Okay, so one moment, I am running out of words. Okay, so we started with the first algorithm that we designed with digital analog techniques was the quantum Fourier transform. And we choose this algorithm because it's a key ingredient for several quantum routines and interesting algorithms. A Fourier transform is a transformation that converts a function into a form that describes the frequencies present in the original function. It is an efficient algorithm for performing a Fourier transform of quantum mechanical amplitudes. And although it does not speed up the classical task of computing this Fourier transformation of classical data, since it enables interesting routines, we think that it is important to study it in the first place. So the way that we have worked was the following. First, the way we proceed was, first we compute the unitary operation that the algorithm performs, and then write that operation in terms of the Hamiltonian. Then, by applying different digital analog techniques, we can simulate that Hamiltonian, which in the end is just an algorithm. So this is the way to link the Hamiltonian simulation with the algorithm implementation using digital analog techniques. So for the case of the quantum Fourier transform, we first compute the unitary matrix that describes the entire process, and express it in terms of a Hamiltonian that was easy to simulate using digital analog techniques. The easier one to simulate is the inhomogeneous Ising Hamiltonian, which is the one that I use as an example of how the digital analog paradigm works and stuff. So some slides before. And this is what we did. So we expressed the Fourier transform algorithm in a succession of unitary matrices that were defined by inhomogeneous two-variation Ising Hamiltonians and single qubit rotations. And then in a following work, we also included a comparison of the performance of the Fourier transform and the different computational paradigms, digital, stepwise, and bank. And we took into account all those sensible experimental errors that we could expect in a realistic experiment. Here are the results that we found. So we apply the Fourier transform to a family of states that is defined in that way. And as a figure of merit, we use the fidelity in terms of the ideal and the noisy density matrix. We took into account the errors that I showed before, and here are the results that we obtained. Let me guide you through this graph. So, for example, let's focus here on the 6-qubit Fourier transform. The worst fidelity is, well, here I am pointing to the fidelity achieved by the digital implementation. Then this is the fidelity achieved by the stepwise digital analog. So the fidelity is much worse than the digital version. And we think that this happened because these 2-qubit gates, that means turning on and off the interaction between 2 qubits, is noisy, but turning on and off the interaction between all of the qubits of the system, which would be what we would do for the stepwise version, is much more noisy than the other approach. So our hope is on the bank protocol, and yay, the fidelity achieved by the bank DAQC is much better than both the stepwise, of course, and also the digital version. And this repeats for the rest of the cases. So in the 5 qubits quantum Fourier transform, the best fidelity is also achieved by the bank DAQC protocol. And in the case of 3 qubits, which is a non-challenging algorithm, but still an interesting one, we see that the best fidelity is also achieved by the bank protocol. So at the side of these results, we see that both the digital and the stepwise protocols get strongly affected by the intermittent switching on and off of the interaction of the system, while the bank protocol, since only face this error at the beginning and at the end of the process, is much more resilient to those kind of noises. So these results make us think that the DAQC paradigm is a useful tool for implementing long-depth quantum algorithms. And that is what took us to study how to use this paradigm to implement a more ambitious algorithm, which is the phase estimation algorithm. So this algorithm is an algorithm or a subroutine. One can choose the words that prefer. And this allows us to get an approximation of the eigenvalue of a unitary operator under some circumstances. So suppose that we have a unitary operator, U, and this operator has an eigenvector, U small, and a corresponding eigenvalue, which where the value of phi is unknown and is not known. So the goal of the phase estimation is to estimate that value. To perform the estimation, we assume that we are capable of preparing the state U and perform the control U operation to raise to successive powers of 2. And this routine, the phase estimation procedure has to be divided into 2 registers. The first register contains a T number of qubits that are initialized in the ground state. And how to choose this T, this amount of qubits, depends on 2 things. First, it depends on the number of digits of accuracy that we wish to have in our estimation of this phase phi. And also it depends on with what probability we want the phase estimation procedure to be successful. We will see this in detail in the next slide. And then the second register begins in the state U. That is why we assume that we can prepare it. And it contains as many qubits as are needed to store this eigenvector U. Then the routine is performed in 3 stages. First, we apply Hadamard gates to the first register, followed by the application of control U operations on the second register with U raised to successive powers of 2. Second, we apply the quantum Fourier transform on the first register, which is obtained by reversing the circuit of the direct quantum Fourier transform, which is the one that I presented previously. And the third and final stage is to read out the state of the first register, just the first register, by doing a measurement in the computational basis. And this will provide us a pretty good estimation of the eigenvalue phi. Before going further into the digital analog description of this routine, I would like to sharpen our intuition on why the phase estimation works. And this will be of relevance whenever I show you the result that we get. So suppose that this phase phi can be expressed in this in a fixed number of bits, this t that I mentioned before. So the binary form of this phi would be 0.51, phi 2, until phi t. Then the state resulting from the first stage after the control U operations may be written in this way. So if we apply the inverse quantum Fourier transform to this state, we get the phases down to populations. So the output state from this stage 2, it would be the product state phi 1, phi 2, phi t. So if we measure on the computational basis, we could get this exactly value of phi in the binary representation. What happens if I cannot express this phi exactly in a binary representation using just t bits? Well, then the success of our estimation will be a little bit worse than if we could express it exactly in the binary basis. And the success would depend on the distance between the phi and the one that we estimated. For example, let's say that we have this unitary operator, P of phi, and we want to obtain the phase phi such that it is an eigenvalue of the eigenvector U. We are choosing to use a 4-qubit register, and the eigenvector is going to be the excited state 1. Then, using the phase estimation, one might get an approximation of the phase phi, which corresponds to 1/3. We choose this example because, although it is a rather simple one, this 1/3 has a periodical binary representation. So, using only 4 bits, we are not going to be able to get the exact value. But we can try to get as close as possible. So, for example, we could get either the 0.0101, which corresponds to 5/16. So this is not the exact value of 1/3, but the relative error of this value is 6.25. So it's close enough, we could say. And the other value that is close to 1/3 in the binary basis using 4 bits is 6/16. And the relative error is much bigger, is 12.50%. So after measuring in the computational value, we could get both states with the probability amplitudes that I show here. So what we want to do is to perform the quantum phase estimation using both digital and digital analog paradigm. And we want to get the probability amplitude of the states that corresponds to these results. And we want to see that for both implementations. Before showing you the results, I am making a little bit of hype. Before showing you the results as we get, let me tell you that in this case, we follow a different strategy. So instead of translating translating the entire algorithm, the entire unitary operation into a Hamiltonian, and then try to optimize that Hamiltonian to get the best digital analog implementation, we did it in a more lazy way, so to speak. So what we did was translate each step from the digital circuit into a digital analog implementation. And for that, we first decompose the algorithm into a new universal set of gates. We choose these rotations around X and Z axis as single qubit gates, and the C0 gate as the 2-qubit gate. And then each gate of the digital implementation has a digital analog implementation. This is not the best way to implement an algorithm, of course, but it allows us to explore more systematic alternative to build digital analog quantum algorithms. So imagine if we get a good enough result using this technique, using digital analog paradigm, since there is a lot of room to improve that digital analog implementation, we can have a taste on what to expect if we are going through the good way, or maybe we have to focus on a different algorithm. So the decomposition using the decomposition of the gates that play a role in the quantum Fourier, in the phase estimation, using this gate, this universal gate set is the one that I show here. So for the single qubit gates, we would apply the same ones. And whenever we see a C0 gate, we will decompose it using digital analog techniques in this set of single qubit gates. And then the evolution, the analog block would be this one, a set-set interaction. So what we are going to compare is the probability amplitude of the quantum phase estimation outcome when we run it following both digital and digital analog approach, the lazy one. To do so, we run the quantum phase estimation circuit from the previous example, where we wanted to estimate the phase equal to 1/3 using a 4-qubit register. We have also included experimental noises following the noise model that we presented previously. And then what we expect to get is the probability amplitude of each state that is as close as possible to the ideal case. So the complete routine has before going further is a long depth quantum algorithm. So there is a relevant number of 2-qubit gates, and it is a demanding task for both the digital and the digital analog implementation. So now going to the results that we get regarding the digital analog implementation, both the stepwise and the bank can reproduce the probability amplitude that we wanted. So we can see that stepwise and bank has a nice value near to 1/3. Also, the digital case works super fine, of course. But this is what I said before showing the results. So there is a lot of room in improving the implementation of this algorithm. We have done the most lazy, so to speak, so the worst implementation possible of the phase estimation using digital analog techniques, and still we are capable to reproduce the results that we want to see. So this let us know that digital analog techniques might be a good alternative for implementing long depth quantum circuits. One thing that I would like to do would be to improve the implementation of this task, and let's see if digital analog can go further the digital implementation. We will let you know in the future. So the next algorithm that I will present you here is the HHL. So this algorithm for solving linear system of equations, and the reason why we choose this algorithm after working on the Fourier transform and the phase estimation is because both the Fourier transform is a part of the phase estimation, and phase estimation is part of the HHL. I will show you in a minute. So this HHL algorithm is an algorithm that solves linear system of equations. So in essence, it can solve any kind of matrix inversion problems. it works in the following way. Given a matrix A and a vector B, it finds the solution of the X vector. The given matrix A and the unit vector B must fulfill those conditions. A has to be a Hermitian invariant matrix and B has to be a unit vector. This algorithm estimates the result of the expectation value of an operator on this X state and is exponentially faster than any classical algorithm. So the HHL can be described dividing it into 3 steps. First, the quantum phase estimation, the one that I presented previously, to compute the eigenvalues of the problem matrix A. Then the second step would be the ancilla quantum encoding that store the inverse of these eigenvalues. And then an inverse quantum phase estimation that reset the register back to the ground state. Also, the qubits of the system are grouped in 3 families. First, the ancilla qubit, which is formed by only 1 qubit, and it is used to store the computed result of the matrix function. Then the registered qubits that encodes the binary expression of the eigenvalues are finally the memory qubits that hold the information of the unit vector B. So before now, I want to go back. Okay. So for the first and the last part of the algorithms, the phase estimation routines, there is a known quantum routine that made possible these steps, which is the one that I presented previously, and it is widely understood. Contrary, for the ancilla quantum encoding step, there was no guidance on how to implement this. In the original proposal of this HHL algorithm, the authors mentioned that this step has to map the inverse computed eigenvalues, which are stored in the state of the registered qubits in a binary form. And these eigenvalues has to be stored into the amplitude of the ancillary qubits in a decimal base. So in the way to do this sounds kind of hard. So in the literature, this step has been done either by introducing classical computation to post-select the data and prepare the ancillary qubit, or by knowing in advance the result that one is going to get, which actually represent no problem at all. So that way one can tailor the ancilla quantum encoding. So the hard task here was first to get a digital and systematical version on how to apply this ancilla quantum encoding, and then translate this digital implementation into digital analog. So the way that we develop this systematic way to implement the ancilla quantum encoding step that we propose, this way is independent of the problem matrix A. So we don't need to know in advance any further information about the matrix A, apart from its form, of course. And this is like the first thing that can into anyone's head, right? To make a lot of multi-qubit gates and control everything and apply a lot of rotations. So this step would be carried out by a succession of two qubit and multi-qubit gates. And this is how it looks. So for a 4-qubit register, we would have a lot of multi-qubit gates. As you might be thinking, this doesn't look easy at all. And indeed, it involves an exponential number of multi-qubit gates to be implemented. So this sounds, so the application of this ancilla quantum encoding step involving several multi-qubit gates lead to exponential increase in the number of gates required for this implementation. So we then follow the work done by Motonen and collaborators, and here they propose a general method to translate a general multi-qubit gate into single and 2-qubit gates. And following this procedure, we could decompose our ancilla quantum encoding step into an exponential number of single qubit gates and an exponential number of CNOT gates. So 2 to the number of register and 2 to the number of register, both single and CNOT gates. This NR depends on the problem matrix and also on the precision that one wants to achieve in the algorithm, similar as what happened with the Fourier transform, with the phase estimation. So following this Moton and collaborator works, we can see that we pass from exponential number of multi-control gates to an exponential number of CNOT gates, which of course it is demanding for both digital, for any kind of quantum platform actually, but at least it sets a way on doing this systematically. So the way to proceed in this step would be to translate each CNOT gate into control set operation so that we can implement digital analog techniques to simulate its 2-qubit interaction. And then the Hadamard gate would be applied by different single qubit rotations. So this is just one half of the Ancilla quantum encoding steps. And to implement the entire block would need an exponential value, an exponential number of analog blocks, and this other number of single qubit gates. So this, of course, is a demanding task. The way to implement this would be not stepwise, but bank digital analog approach. So letting the interaction on during the whole process. So as I was mentioned, this is of course a demanding task, but at least we have a way to implement this entire algorithm using digital analog techniques. There is another option that we suggest to implement this algorithm, which is instead of applying the phase estimation at the beginning and at the end of the algorithm, instead of using the approach that I showed previously, which is the worst approach and that can lead to a lot of errors, we can use the first paper that I mentioned in this presentation, the one by Adrian Parra and collaborators, and assume that if the matrix A admits the composition in M body, where M is much smaller than the dimension of the matrix, we can upload the matrix efficiently using the techniques that they use in these problems, in this paper, and implement this in a more efficient way. Then the Fourier transform would follow from the first paper that we published and the first thing that I showed here. And then the Ancilla quantum encoding would be this large amount of single qubit gates and digital analog interactions. So one work that is still missing would be to run the simulation of this problem, but of course this is a really demanding task for both digital and digital analog implementation. So we have not done this yet, but this would be an interesting work for the future. I have no result to show here, I am sorry. And with this, I come to the conclusion of my works. I need a little bit more water. I am sorry, I'm getting dry. So one thing that we are happy about the digital analog work that we have conducted during this year is to see that different universities, different groups from different universities have adopted these techniques and these proposals, and they have continue their work in researching the field of quantum computing. So in 2020, Babukin and collaborator, they use Qiskit Pulse, which is this platform of IBM quantum computers, to implement the quantum Fourier transform work using digital analog approach with Qiskit Pulse, and they saw that it is possible to implement it in superconducting circuits, quantum processors. Of course, the results were good in the sense that they could perform it, they could implement the algorithm, but not good enough in the sense of the results that it gets. They are still noisy systems, and they are not optimized to perform digital analog operations, but at least it is possible to do this implementation, which is something that has to be taken into consideration. Also, in 2022, the group of Yang Wei Pan they include digital analog quantum neural network inside a big project they had. So I'm sorry. Let me start again. So in 2022, Yang Wei Pan and collaborators, they use a 61 qubit quantum processor to perform an algorithm with a neural network, and they include this. I am sorry. Let me go a little bit further. Let me jump to the conclusion, if you don't mind. So the paradigm, the digital analog paradigm is, we have shown that it is a promising approach for quantum computing, and it is capable of achieve good results and good performance in these NISQ devices. We saw that the 2-qubit gates are source of relevant experimental noise, and they accumulate during the entire process. And the digital analog constitute a way to substitute the error that this arises, but by getting advantage of this interaction. Sí, Javier.
Sí, dime.
No sabía si me habías dicho algo, perdón.
No. Termina.
Vale. Well, as I was saying, I will skip ahead until the end of the presentation, just to wrap up everything. So we have shown different quantum algorithms that can be run using digital analog techniques, and we have shown that the result that we had achieved during these years suggests that this is an approach that it is good to take into account in order to use current technology, which is still noisy, of course, but at least allow us to have some results on the experiments. And I think that the next step would be to take this implementation of algorithms into real quantum system, and let's see if we are able to fulfill the results that we say that we are going to get, and also to see if we have room to make much more improvements on these implementations. And with this, I conclude my talk, and I am here to listen to your questions.
Thank you, Anna. Thanks a lot. We hope we're glad that you survived till the end.
Yes, I am sorry.
I imagine what's going on around there. Good. So please, the stage is there, and we would like to hear questions if there are. Feel free to raise your hand and unlock your microphone. Okay, I think this is a very suggesting topic. I have lots of questions, but I don't want to take the the lead. Nobody around? So I'm really curious, Anna. So this icing Hamiltonian, how do you manage to implement it? How do you implement this, the icing, the one you use for the continuous in a superconducting conducting? How do you tailor that Hamiltonian?
Well, first you have to. Well, as I'm going to share the screen once again, so I can go to that.
Yeah.
I think over here, right? It was the.
Yeah.
More or less. Oh no. I have a lot of animations. So. Okay, so once you have the description of the entire, so first, Okay. Once you have, you know, the interaction Hamiltonian of the quantum platform. Ah, no. I am sorry. Okay. This is what I wanted to show. So in the end, the entire problem reduces to find, to solve this linear system of equation maps. So for example, in this case, in this example, once you have this relation between the linear combination of time in front of each two-body term, you just have to solve this linear system of equation, the one that I have in this gray square.
This I understood.
Okay.
This I understood. I want to know how you make up the Ising Hamiltonian. How you bring your system to interact, your 3 qubits to interact through the Ising Hamiltonian.
Okay. That depends more on the experimental platform that we are working on. So for example, in superconducting circuits, nowadays it's much harder than it used to be, since now the aim is to have them isolated enough so they don't interact among each other. So now in superconducting circuits, this could be hard. But for example, if you think in trapped ions, if you put the same, if you make the 3 ions interact between each other and you put the same resonance frequency, there will be the interaction. Or in MB centers, of course, MB centers would be a different platform, but it's the same when you are in resonance with the three, in this case, MB centers or qubits, so you set the same resonance frequency.
So this was my question. So in superconducting, you were previously using some kind of residual interaction that was there, and now but this residual interaction might not be exactly this homogeneous Ising model. Can be an inhomogeneous Ising model. So
yes, of course. We choose to explain the whole digital analog using this homogeneous Ising model, but of course, in a real scenario, even though with this residual interaction among the qubits, this could be not the case, but it's much more easier to get this explanation with 3 qubits in less than 5 minutes if we assume that the interaction is homogeneous rather than if not. But there is another work done by Asier Galicia that has a systematic approach on how to build this homogeneous interaction up from any kind of interaction in the quantum system.
So, and what is the most promising platform? So how about Rydberg atoms, for example?
Yeah, that is the one that is like in everyone's mind nowadays, I guess, right? Because of this new paper that has been published lately. The thing is that you need a platform that you can make the whole system interact at the same time. So if with Rydberg atoms you can do that, then that would be a nice platform. I am also thinking on trapped ions, or any kind of platform that is, instead of trying to isolate the qubits of the system, it get advantage of making them interact together. So I would say both Rydberg atoms and maybe trapped ions.
Yeah.
And also, of course, maybe using NMR and molecules. This is not scalable. That is the problem with these things. But for making some experiment, I would say yes, these 3 platforms. Of course, yes.
Yeah. Okay. So I'm done. So if nobody's curious to have any question, so we will thank Anna again for sharing this time with us. And let me just say that next week will be our colleagues from PyQST who are going to foster a seminar, and we'll be back in 2 weeks with another awesome seminar by Luis Massanes. And so stay tuned and keep in touch, and have a nice week, all the rest of you. So thank you, Anna, and goodbye.
Thank you for having me. Bye.
Goodbye, everybody.